Module 1 introduced us to the mole, among other things. There, we performed calculations to move us from what the chemist could measure on the macro scale to the level that the chemistry occurs, or the nanoscale. The mole was the glue in those calculations. While the mole is inherently a quantitative tool, it is also key to our understanding of chemical reactions and how the amounts of substances present in a process come together to form new substances. In this module, we're going to work with chemical equations, and in doing so, we will expand our definition and understanding of the mole. By the end of this section, you should be able to balance an equation. But first, we need to discuss the importance of these equations and provide some basic info about them. By definition, a chemical equation is a statement that includes both the identity and the quantity of substances involved in either a chemical or a physical change. Equations have a dual nature. They are exceptionally quantitative, and they're going to be used to aid in calculations in our next module. But they're also literary in the sense that they tell the story of chemistry. Think of individual elements, or better, their symbols, as our letters. If that's the case, then chemical formulas are our words. And when those existing chemical formulas come together to create new and different chemical formulas, now we've built a sentence. These sentences start with our reactants on the left side of them. The reactants are the species that come together and are present before the chemical or physical change. Products are formed and are present after that change, and they appear on the right of your equation. Reactants are converted to products, and that conversion is represented with that reaction arrow. There are a few different arrows that are included in chemical reactions. The one given here is the simplest and in a lot of ways the most final. It has a single head pointing in a single direction, indicating that this process started with nothing but reactants and will end with nothing but products. Eventually, you'll learn that the majority of our reactions shouldn't be represented with this arrow because products can also come together to reform reactants. But the single-headed arrow is sufficient for the majority of Gen Chem 1 as it greatly simplifies things. Perhaps the chemist mixes hydrogen and fluorine, both of which I hope you remember are diatomic elements. Both of these elements are reactants in the chemical process. If mixed under the right conditions, these two reactants will form the arrow hydrogen fluoride as a product. These 2 moles of hydrogen fluoride are products. The first, and honestly probably the simplest thing that you'll need to be able to do with chemical equations is to identify the species that are reactants and the species that are products. While it might seem straightforward, ensure that you do some practice so this is super solid come quiz day. Our chemical equations offer more information than just what is reacting or being formed. They also tell us the relative amounts of things being consumed and things being produced. This is where the definition of the mole expands, because one of the mole's biggest jobs is to help the chemist clarify the amounts of something taking part in a chemical reaction. The explanation that follows will focus on values present in this already balanced equation. Try not to worry too much right now about why those numbers are what those numbers are. Our goal in this first subsection is to worry about what those numbers are. We're just picking apart equations at the moment. We're not trying to balance them yet. Remember when we combined the idea of the mole with the subscripts in our chemical equation so that we could say super useful things like there's 2 moles of hydrogen atoms for every 1 mole of hydrogen molecules? Well, we can do something pretty similar on this larger reaction size scale. If our elemental symbols are the letters of chemistry, then these subscripts indicated with this purple arrow in a chemical formula indicate how many of that letter appear in your word. To instead indicate how many times a word will appear in your sentence, we turn to the numbers in front of the chemical formula. We can't use the subscripts to describe how many of a compound there are because they are already telling us how many atoms there are. These values in front of the reactants and products are referred to as coefficients. The chemist reads their coefficients as mole quantities. Notice that I've included 3 arrows here correctly, but only one is pointing to an actual number. That's because the chemist does not write in the 1 if only one of that substance is required to obey the law of conservation of mass. This is the case with the hydrogen and the fluorine. We say that the 1 is implied here. The simplest use of our coefficients is to indicate how many of a type of thing are present in your reaction. For this particular reaction, I know that there is 1 mole of elemental hydrogen because of that implied 1 coefficient in front of the H2. I also know that the reaction will require 1 mole of fluorine because, again, there's a coefficient of 1 associated with the F2. Similarly, I could say that I require 2 total moles of reactants for this reaction, 1 mole of each of them, or that 2 total moles of products are formed during this reaction, or that 4 total moles of substances are required for this reaction to proceed as written. The coefficients in a balanced equation can also be used to equate the amount of one substance to the amount of another substance that takes part in the same process. Based on the coefficients in this equation, I could say that 1 mole of hydrogen reacts with 1 mole of fluorine, or that 2 moles of hydrogen fluoride will form from a single mole of hydrogen, or from a single mole of fluorine. Now, I'm sure half the class is wondering why it sounds like I'm repeating myself. Being able to relate the coefficients in a chemical equation is the basis for stoichiometry, which we see in Module 3. It is a very important skill, one of the few things that transfers to each and every chemistry class ever, and really a lot of science classes, as any chemical process in biology, physics, etc. involves coefficients and mole ratios. But it's not intuitive to all. Even though you won't quantify amounts of reactants and products for another module, it's worth getting in the habit of thinking in those terms now, so it's more natural when you do have to tackle it. So, why does the chemist use the mole to describe their chemical reactions? Lots of reasons. As we'll see in Module 3, we can't use mass, as our substances will likely have different molar masses, so the count of molecules is different for each and every substance, even if it has the same mass to begin with. The mole translates from one sample to another because it's just a universal count of particles. But since the mole is our bridge between the nano and the macro scales, it allows us to prepare one sentence that describes what is happening on both the scale the chemist can measure things, or the macro, and the scale where the chemistry actually happens, or the nano. Maybe the chemist is running this reaction on the mole scale, so they measure exactly 1 mole of H2, which will have a mass of 2.02 grams based on the molar mass from the periodic table. And then they measure exactly 1 mole, or 38 grams of F2. They mix that, and they should expect to recover 2 moles of HF, which would have a mass of 40.02 grams. The reaction itself would occur on the nanoscale, where 1 mole of H2 would come together with 1 mole of F2 to form 2 molecules of HF. The simple, balanced equation tells both versions of this story pretty well. 2 more quick points to wrap up this video, both of which will be hugely important to remember as you start to balance equations in the next subsection. First, we cannot, and under any circumstances, violate the law of conservation of mass with our equations. There have to be the same number of each type of atom on both the reactant and the product side of this reaction arrow. Otherwise, we're creating or destroying atoms, and we are not capable of or allowed to do that. We're usually going to have to do some work to ensure that we obey this law and that our equation is balanced. And when we do that work, we have to keep in mind that our chemical formulas in our equation cannot change once they are part of our reaction. If we change a subscript in a chemical formula, we are changing the identity of that compound. Take the difference between CO and CO2 as an example. If you change the subscript, you're changing the amount of times the letter appears in that word. That then changes the word. You have to keep the subscripts the same so that we have the same chemical compound. So instead of changing subscripts to balance an equation, the only thing you can play with are the coefficients. We can make the coefficients whatever they might need to be to get our atom count even, but we will never, ever, ever, never change the subscripts in a chemical formula. For example, we can't just double the subscripts in the HF here. The 2 HF in the correct examples represented 2 molecules in which 1 hydrogen was bound to 1 fluorine. This is, in fact, what happens in this reaction. This oh so terribly incorrect H2F2 represents 1 single molecule that involves all 4 atoms bonded together. These 2 products are fundamentally different, so much so that one exists and the other one doesn't. So it's really important that you only alter coefficients when balancing equations.